Kia ora koutou. Welcome to this next Chemistry 2.4 video where we look at the energy changes of a reaction and we calculate the energy change of a reaction by using what is called bond enthalpies. So a bond enthalpy is the amount of energy that's required to break 1 mole of a bond. So let's say we had, for example, a hydrogen gas molecule. So the bond there is hydrogen to hydrogen. What has been calculated in laboratories is how much energy was required to break a certain number of these molecules, and they found an answer in kilojoules per mole. And what they found was to break 1 mole of this molecule, it required 435 kilojoules per mole. So what we can do with these numbers is that if we have a chemical reaction, we'll write out a chemical reaction now. So let's say we had hydrogen gas H2 plus Cl, chlorine gas Cl2 going into hydrogen chloride. We can use a table that show us the values of all of the bond enthalpies within each of the molecules. And we can use that to work out how much energy would be released or absorbed in this reaction. So to do that, we first of all need to be able to work out how many of each type of bond are in this reaction. So what we do is we need to draw out the Lewis diagram. So we've already done the hydrogen Lewis diagram there, but we'll just do that again. So we've got hydrogen, one hydrogen molecule, plus, so we're effectively just drawing out this chemical equation again, but with Lewis diagrams instead of their chemical formula. Cl to Cl. I'm not going to worry about the valence electrons. And that goes into 2 molecules of hydrogen chloride. And so I'm going to draw both hydrogen chloride molecules to make counting up the number of bonds easier. So what we can do is count up how many of each bond there are, and then we enter our we enter the number of bonds into this formula, which is the change in enthalpy of a reaction. So delta RH equals the sum, so we've got the sigma sign, which means sum. So the sum of the bonds broken minus the sum of the bonds formed. So minus the sum of the bonds formed. Just written that out there. So that makes sense because to break a bond, we need to input energy. So if we're breaking a bond, we're inputting energy for these hydrogens to have enough energy to then break apart into their own individual atoms. So that requires the input of energy. And then when new bonds are formed, energy is then released. And so we've got a negative number for the change in enthalpy. So remember that in endothermic reaction, one that absorbs heat, which is the breaking of bonds, requires a positive enthalpy, so that's why we'd have a positive number here. And then we add the negative sign because heat is going to be released here. And so if we calculate using the tables that we would be given to us in an exam or in your textbook, we can work out the change in enthalpy of the bonds broken minus the enthalpy change of the bonds formed, and then we get the change in enthalpy of the whole reaction. So to calculate this, we need to know the bond enthalpies of each of these bonds here. And so I've got a table next to me, so I'll write above each of the bonds what their bond enthalpy is. So we've got 435 for the hydrogen molecule, 435. For chlorine gas, we have 243. 243. And for the hydrogen chloride, it is 431. 431. So what we're going to do is take the sum of the bonds broken and the sum of the bonds formed, and then go the bonds broken minus the bonds formed. So to calculate that, we go 435. So I'll just put it in brackets. 435 plus 243. So, and what's helpful for our working as we go through is to cross out all of the bonds to make sure that we include them all in our calculations. So we're going to go, so that's 435, and there's only one hydrogen to hydrogen bond. There's only one chlorine to chlorine bond. So we've only got 1 times each of those numbers. That's the sum of the bonds broken, and then the sum of the bonds formed. We count up the number of hydrogen to chlorine bonds there are, and there are 2. So we're going to go 2 times this value here, 2 times 431. 431. And then we add all those together, and then we get our answer. So we'll do that very quickly. And that equals negative 184. 184 kilojoules per mole. So we can go mole minus 1. So for each mole of these molecules, we are going to end up with, of this reaction, we're going to end up with 184 kilojoules per mole. And because this is a negative sign, that means energy is going to be released into the surroundings. So this is an an exothermic reaction because heat is being released. So we'll have a look at a past exam question, which is slightly, we'll get rid of these, sorry, which is slightly trickier because we need to rearrange the formula a little bit. But this is a typical exam question. So when propane C3H8 is burned, it reacts with oxygen in the air to form water, H2O gas, and carbon dioxide, CO2 gas. So we've got this propane plus oxygen goes into water and carbon dioxide. And it tells us, in this case, it tells us a change in enthalpy of the reaction. So for this question, they're asking us to calculate the average bond enthalpy of the carbon to oxygen bond, and this is a double bond, using the data below. So we still use the same formula that we had before. I'll just copy and paste that in. And then we go about the same way for answering this question as we did in the last, for the last one. So we've got, what we need to do is count up the number of each bond, so we can put in the values into this equation. So to do that, we've got, so it's negative 2056, negative 2056 is equal to the bonds broken. So we've got 1 molecule of this propane. And so when it's in a complex Lewis diagram, or in this case, they've just done them all, they're not testing you on how you can do Lewis diagrams. They're testing you on the calculation. So you'll always be given a Lewis diagram that you wouldn't know how to do. So this propane, which we'll learn how to do in the organic topic, but we don't know how to do it in this topic. So they'll give you that Lewis diagram, and in this case, they've given us the other ones as well. So that's all fine. So we need to count up the number of bonds that there are that are broken. So we've got the carbon to hydrogen bond. So because it's 1 propane molecule, you've got 1, 2, 3, 4, 5, 6, 7, 8. So we're going to go 8 times the carbon to hydrogen bond, carbon to hydrogen. So the sum of 8 times that, plus, there's also 2 carbon to carbon bonds there, 1, 2, plus 2 times carbon to carbon, plus, these are all the bonds that are being broken, we're counting them all up, plus 5 O2. So we're going to have 5 times these, so we've got 1, and then 2, 3, 4, 5, so we have 5 times O, and all of that, so these are all of the bonds broken, we're then going to go that minus the bonds formed. So we've got 4 water molecules, so 1, 2 for each one, so 2 times 4, 8, so there's 8 oxygen to hydrogen bonds, 8 times O to H, put this all in brackets, plus 3 carbon dioxide molecules. So there's 3 carbon dioxides, 2 carbon to oxygen double bonds for each molecule. So you go 2 times 3, so there's 6 carbon to oxygen bonds in total. So 6 times carbon to oxygen. And then we need to just plug in all of the formula, all of the values. So this equals 8 times C to H, which is 413, plus 2 times carbon to carbon, which is 348, 348 plus 5 times O to O, which is 495. I will just pause this and then we'll end up with the total values. So be back in 1 second. Okay, so I've just drawn all of that out here. So what we've ended up with is negative 2056 equals the sum of the bonds broken, which equals 6,475. So that's all, the working is all up here, minus 8 times 463, which is 3,704, plus 6 times the carbon to oxygen bond. And that's the bond enthalpy of this bond that we're trying to find. So we don't know the value there. So now we just need to use some algebra to rearrange this equation and work out the value of that bond there. So we can first of all put this value onto the other side. So we minus 6,475 from each side. So that's going to equal 2,056 minus 6,475. Just 1 second. Minus 6,475 is negative 4,419. And that equals negative 3704 plus 6CO. And so now we can plus 3,704 onto the other side. So we'll do that. 3,704. Oh, excuse me, I've done the wrong, got the wrong value. So I've just fixed that up here. So it should have been 8,531 here, because I should have done negative 2,056 minus 6,475. And then if I go that value plus 3,704, then I get negative 4,827, and I can cross this off that side. And so what we end up with is this value minus equals negative 6 times the carbon to oxygen bond. So we can divide both sides by 6. Divide both sides by negative 6, divided by negative 6, and that will equals 804.5. So we can say 804.5 kilojoule per mole equals the carbon to oxygen bond. So we'll change this to 3 significant figures and then add units and then change it around so it's more easier to read. So the carbon to oxygen bond equals 805 kilojoules per mole. So I hope that helps you with working through a past exam question for bond enthalpies. I know it's a little bit messy with the writing tool that I have. I'll need to get a better writing tool so we can get through this a bit quicker. But thanks very much for watching. Next video we'll look at further into the energy changes of reactions and more calculations. So see you next time.